of rotation. So we will mainly focus on the case of 3 dimensions, but before we do that, I want to talk a little bit about the geometry of space. Right. So the geometry of space is encoded in something called the metric. And basically it tells you how to measure distances and angles and things like that. Okay, so basically the distance between 2 points, one which I'll just call x, and x plus dx. So x is here, x plus dx is here. This is dl. Okay, so if you're in, for example, if you're in 2 dimensions, it's easy to see that, for example, if this is x1, x2, and this is x1 plus dx1, x2 plus dx2, then the Pythagoras theorem will tell you the base here is dx1, the height is dx2, and therefore the length over here, or the length squared here, is just given by Pythagoras theorem, dx1 squared plus dx2 squared. Okay, so this is in 2D. If you're in d dimensions, then you can guess that Pythagoras theorem will still apply, and the answer will simply be given by the higher dimensional version of Pythagoras theorem. So dl squared will simply be dx dotted into itself. Okay, and what if you use index notation? This can be written in terms of the Kronecker delta. Right. So dx dot dx is simply dxi summed over I. That's what the dot product means if you're using Cartesian coordinates. And so you can use the Kronecker delta and say that this is Kronecker ij dxi dxj. Okay. And so the metric Gij is generally defined as the coefficient of xi and xj. So the L squared is in fact Gij, let me use y, I, yj, and the coefficient of the quadratic form is in fact Gij. So in this case, because we're using Cartesian coordinates and we're in flat space, the metric is just given by the Kronecker delta. Okay. So this is not a course on differential geometry, but I want to talk about it because we're going to switch to spherical coordinates in a little bit. And there, it would be useful to know how to do the calculation using the metric. But I don't quite know why it's not taught. So it's not taught very widely, which is very strange to me. So what we're going to do, firstly, is to recognize that the Euclidean, let me just say, translations plus rotations, which is often called the Euclidean group. But it's okay if you don't want to remember that jargon. But just remember, translations and rotations actually preserve the metric. Preserve the flat metric. So what does that mean? So you can think of Kronecker delta as, in fact, the object that tells you how to measure distances between dx and dx, sorry, x and x plus dx, right? So if I give you the infinitesimal displacement, the metric tells you what length does that correspond to, because all you have to do is just contract your dx with the metric, right? Just like that. So if it was something else, then it will give you a different answer. But if it gives you the same thing after you do a transformation, like what we're about to do, then it tells you that the way you measure lengths in the same, the way you measure lengths after you do the transformation will be the same, right? So in particular, what I'm talking about is translations and rotations here, which means the following. So if I start with x, then rotations, as you know, is implemented through a rotation matrix. So let me call it, the new coordinates, let me call it x prime j plus ai. So this is a constant. Okay, and this, in fact, corresponds to translations. Right? So if I don't have a rotation, if rotation is 1, then it will be x equals to x prime plus a, which means I just shifted everything by a. But now I also have a rotation matrix. Okay, so that's the most general form of the combination of both rotations and translations. So I can take the d on both sides. So the infinitesimal version of this will be simply dxi equals to r hat ij dxj. Okay, and a is a constant, so it drops out when I take the infinitesimal, right? And so now I can plug it into this guy here. Okay, so what is dl squared? Well, dl squared is given by Kronecker ij dxi dxj, but now we can plug in the new definition. I'm sorry, this is x dx prime, right? I'm going from x to x prime. So this will be now Kronecker ij, now r hat a dx prime a, and then r hat j b dx prime b. Okay, all I'm doing is just plugging in the definition, plugging in this result over here into the d-axis. But you notice this is nothing but the original definition of the rotation, what rotations mean, right? This is the orthogonal condition, meaning this should give you identity. So in case it's not clear, this is in fact identity. Kronecker delta is identity times r hat and then r transpose. And this is asking for the AB component, dx prime A, dx prime B. Okay? But this is orthogonal by definition of the rotation matrix. So this is just identity. Kronecker AB, doesn't matter whether I use AB or IJ, so let me use back IJ, dx prime I, dx prime j. Which means what? Which means that even after rotations and translations, if this is how I measure length, then this is also how I measure length, right? Of course, dxi is not the same as the dx prime I. It's not the same because they're rotated. They're rotated relative to each other. But the way you measure length is the same, right? It's just basically given by Pythagoras theorem. So this is what it means to preserve the flat metric, meaning it doesn't change. How you measure the length remains the same, even though I've rotated the coordinate system. Okay, and that's of course not surprising because all I'm doing is I'm taking flat space and I'm rotating it. Right? It doesn't matter, but we all know, I think we all have a good intuition that it does not matter how we rotate the room. The ruler, right? If the ruler is 1 meter, if I rotate it, it remains 1 meter. So, but this is kind of a mathematical way to encapsulate this, right? Of course, it's not just for this reason that I'm talking about it, but certainly this is yet another way to talk about the symmetries of space, right? The symmetries that we've been talking about, namely translations and rotations. Now, so when we talk about three-dimensional space, in particular, we like to also use spherical coordinates. Okay, spherical coordinates. And this is also where the metric, this is yet another reason why I'm talking about the metric, because once you know your geometry, then going between different coordinate systems just means the formula. You start, usually, as a practical strategy, you start with a Cartesian system, and then you switch to whatever coordinate system you want through a definition like that. Right? It won't be the same, but basically once you define your coordinate transformation, then you just plug it into the Cartesian definition, and you can find a new metric in the new coordinate system. So in the spherical coordinate system in particular, let me just draw the picture first, and then we can talk about the trigonometry. So if you're in 3D space, then the reason why we want to use spherical coordinates is so that we can exploit the spherical symmetry of space, right? So there will be spheres of constant radius. So you foliate space, that's how the mathematicians would phrase it. You foliate space with spheres of constant radius r. And of course, if you want to have that, then you will need to introduce, so this is r. And then this angle is theta. Okay, and then if you draw a perpendicular to the 1-2 plane, then the angle that this line makes with the one axis is called phi, right? And this is of course also perpendicular. So if you think about the trigonometry of this, the z-axis, or the third axis, is just a projection of this length on the z-axis. So the x3 is easier to figure out. It's just r cosine theta, okay? And then this length here is r sine theta, which means that this is r sine theta, right? This is the parallel transported version of this guy. So this is r sine theta, and if this is r sine theta, then this guy here is r sine theta and then cos phi, and then this is r sine theta And then when you project it onto this, the two axes, that will be r sine theta sine phi. Okay, so this r sine theta. If you start with the third axis, then you can easily remember this will be sine theta, this will be cos phi, and then x2 will be r sine theta, but now you project it on the adjacent side. So it will be, one will be cosine, one will be sine. So if you try to do that, then of course, if you take the d of this, it gets a little bit messy, right? So for example, dx3 will be a little bit messy. It will be dr times cosine theta minus sine theta d theta times r, and so on, right? So actually I won't look it up, but what you want to recognize is that actually you can do this and plug it in by brute force, but what I recommend doing instead is to recognize that when you now plug this guy in, what you have is you now just do a Jacobian, right? So you have dxi, d, and then now the new coordinates are r theta phi of a, dxj, let me just write it as this guy, and then d, let me define the coordinates, the new coordinates first. Okay, so let's call the new coordinate system C. Ci is r theta phi. Okay, so you start with dxi, dxj, connector ij, and so when you plug this into that, you need to do a chain rule, dxi, dca, dca, right? So this is dxi, and then dxj, dcb, dcb, connector ij. So this is dxj, and then when you collect the terms, you find that you get dca, dcb, and then actually this will be dxi, dca, dxj, dcb, connector ij. Okay? And basically this is just a dot product because it's a connector delta, so it's just dx, dca, dotted into dx, dcb, dca, dcb, and in fact this object here is now the GAB in the C coordinate system. So what you want to realize is that if you actually carry out the derivatives, so you just need to do dxr, dx dr, dx d theta, dx d phi, and what you realize is that dxr, for example, is in fact just a unit vector in the radial direction, r hat. And then dx theta is in fact the theta hat direction times r. And then dx d phi is in fact r sine theta times phi hat. Okay, I won't derive this, but you can check this for yourself. It's just calculus. So if you just plug it in, do the calculation yourself, you will find that that's in fact the result. So once you recognize that, then you realize that all these guys are orthogonal to each other, mutually orthogonal. So when you carry out the dot product here, in principle, you need to do the r theta theta r, phi, theta, theta phi, you know, you have a 3 by 3 matrix by running CA and CB over all the r theta phi, right? But because they're all orthogonal, the only thing you need to dot is with itself, okay? So this ends up being, so let's start with RR. So you get dxr dotted with itself, so squared, dr squared, and then dx theta, d theta squared, and then dx d phi squared, d phi squared. Okay? Again, because of orthogonality, right? Because dx dr theta phi are mutually perpendicular. That's why you don't have to care about the cross terms. Otherwise, you will have terms that go like dr d theta, dr d phi. Here you will have d phi, d theta d phi, and so on, right? But you don't, because they are all perpendicular to each other. So what is it? So this is r hat dot r hat, which is 1. Dx d theta is now r squared, and then theta hat dotted into itself is 1. And then this guy is r squared sine squared theta. And then again phi hat dot phi hat is 1. And in fact, you have dr squared. Let me just package it a little bit. R squared d theta squared plus sine squared theta d phi squared. Okay? So what you notice is the following. If because of the way I parameterize my 3-dimensional space, if I focus my attention on only the sphere of radius r, in other words, I don't try to live off the sphere, I just want to live on the sphere, then I set r to a constant. Okay? So then this in fact, you can think of it as the metric on a sphere, as a two sphere because it's a 2-dimensional surface of radius 1. Okay, and then if you want to get the sphere of radius 10, just multiply by 10 squared here, or whatever r squared, whatever the radius is, squared in front, right? But otherwise, this guy itself, you can think of it as just a metric on a sphere of radius 1. Okay? So why am I talking about this? So one of the things that we will talk about is how does the momentum, linear momentum operator, how is that related to the angular momentum operators? Okay. So what we will discover later on, so we need to do two things. One is to show you how to get the momentum squared operator from the metric. That I'll just have to tell you because it takes a little bit of differential geometry to explain. So let me do that right now actually. So remember that p squared, this is the linear momentum, where p is the linear momentum. So p squared psi So psi can be any arbitrary state. This, remember, is minus Laplacian acting on x psi. Okay, and in Cartesian coordinates, we know how to do this. This is just minus partial I, summed over I, x psi. In fact, that's how we go from here to here. That's how we figure this out. But as I told you before, we need to write physics in, we should be able to write physics in any coordinate system we want. Okay, so in other words, when we write down an expression and it has some physical application, it better be that the expression can be converted to any other coordinate system. Okay? So the best way to do that is to use a language that allows you to do this translation between coordinate systems as efficiently as possible. And that's in fact that's the language of differential geometry. Differential geometry, in fact, a lot of it, not all of it, but a lot of it is actually just nothing but the language of using arbitrary coordinate systems to describe distances and derivatives and stuff like that. Okay. So, unfortunately, I can't tell you the next step, how I derive it, how I show you that. I can't show you why it is the case, but let me tell you how to do it. Okay. So, this is in Cartesian coordinates. In any other coordinate system, then what you do is the following. Let me write down the formula and I'll explain to you what it means. You take 1 over square root g, and then partial I, square root g, and then gij, partial j, and then x psi. Okay, so in other words, what I'm saying is that the Laplacian, the negative Laplacian, always takes this form. So let me explain term by term what this means. So you already know the metric. Okay, so step 1, you take the metric and calculate the determinant. Okay, so G with a double line is just nothing but the determinant of Gij. Okay, and then you take the square root. So do you know how to calculate this? You know how to calculate this. And then step 2, you calculate the inverse. So Gij upstairs is not the same as Gij downstairs. Gij upstairs is just nothing but the inverse, which I'm going to write it in index notation. So this is G inverse times G, and I'm asking for the IK component of that. So because it has to give you the identity, so it gives you Kronecker IK. So i.e. Gij with upstairs index is the inverse of the metric. And once you know how to calculate that, then we know how to do this, how to at least. So, for example, let's in fact make sure that I can actually recover this formula, right? So, for example, when Gij is just Kronecker Ij, what does that mean? It means that it's just a matrix 1, 1, 1, and 0 everywhere else. So of course that means that the inverse is just, again, just the identity. right? If the inverse of the identity is the identity. And then the determinant, so make sure you take a determinant of the metric, not the inverse, because the determinant of the inverse is 1 over 1 divided by the metric determinant. So determinant of the metric is now just 1, right? So therefore you can plug it into this formula. So Laplacian on your wave function is just 1 over square root of 1, and then partial I square root of 1, Kronecker ij, and then partial j, and then psi. Right? Square root of 1 is obviously 1. Oh, I should say, but this is the positive square root. Right? This came up in our class, I think last week. Square root, in general, has a multi-value, it's multi-value, but in this case we mean the positive square root. So, so then this just gives you Kronecker ij, partial I, partial j, acting on the wave function, and that of course is just this guy over here. Okay? So let's in fact calculate what would it look like in spherical coordinates. Okay, and then so we'll calculate it, and then maybe I think we might run out of time, but the next time I'll relate it to the angular momentum operator. So now let's do spherical. Let's do the spherical coordinates. So this is Cartesian, right? And this is now, let's try to do spherical. Okay, so now Gij is a little bit less trivial. Is 1 r squared sine theta squared. S theta is sine theta squared. S theta is S sine theta, and then we want to square it. And it's 0 everywhere else. And the way you arrange your rows and columns, here we have to be a bit careful to specify that, right? So this is the R column, that's the theta column, this is the phi column, this is the R row, right? And this is the theta row, this is the phi row, okay? And so the way we do it is just by chronology, R, theta, phi, okay? But now all I'm doing is just reading off the metric, right? Reading off the metric, GAB. So this is GRR, G theta theta, G phi phi. Maybe I'll write it down so that it's clear. GRR is, let me do it over here. So GRR is 1, G theta theta is R squared, and then G phi phi is R squared sine theta squared, right? And everybody else is 0. So this guy will now look different because, well, what's the inverse? For example, the inverse is simply this guy, but all the diagonals flipped in terms of taking the reciprocal, right? So if you have a diagonal matrix, the inverse is just take the diagonal components and take the reciprocal. Right? Okay, so I'm going to erase this so that it won't be confusing. So 1 over r squared, 1 over r squared sine theta squared. Okay, and it's still 0 everywhere else. Well, and then the determinant is, again, it's a diagonal matrix, so it's easy to take the determinant. Just take the product of the diagonal. So 1 times r squared sine squared theta. And so in particular, the square root of the determinant is just r squared sine theta squared. I should make a remark. Again, I won't prove it, but dy times square root of the determinant of G is in fact what in multivariable calculus we call d of the volume. Okay, so the infinitesimal volume element is in fact can be written in a very general way once you know the metric. Just take the square root of the determinant and multiply by the coordinates, and that will give you the volume. So for example, you might recall that the d volume in spherical coordinates is in fact r squared sine theta times dr d theta d phi. How do you know that? This is there's no square here. So how do you know that? In fact, you see that this factor here is in fact just root g, right? It's just right here. So it's very easy to calculate things related to geometry, or at least be able to write down the right thing to calculate once you know your geometry. Okay. So, but anyway, so this is just something to know about. But now let's calculate what's the Laplacian on our wave function. Okay. So now we have 1 over root g, which is r squared sine theta, and then I and jj means I'm going to sum over all the coordinates, but remember that this is a diagonal matrix. So ij really runs over rr, theta, theta, and phi, phi only. So let's do it. So it's dr, and then root g is again r squared sine theta, and then grr upstairs is 1, and then dr. Okay, plus 1 over r squared sine theta. The next coordinate is d theta, r squared sine theta. So you always have a root g, and then now d theta theta, g theta theta is now 1 over r squared, and then d theta psi. Okay, and plus 1 over r squared sine theta, d phi, r squared sine theta, and then now g phi phi is 1 over r squared sine theta squared, d phi psi. Okay, and finally we should simplify things a little bit. These are r derivatives, so the sign will cancel out. Okay. These are theta and phi derivatives, so the r squareds will cancel out from here and here, here and here. Okay, but there's a 1 over r squared here, so I can factor that out. So it looks like that 1 over r squared dr r squared dr psi. Okay, and then plus. Also, you know that this is 1 over length squared, where the Laplacian is 2 derivatives, so you know it's a 1 over length squared. So you can, if you want to check your calculation, you can just count the lengths in this problem. So for example, r squared and r squared will cancel out, and then you have 2 derivatives with respect to r. Here, the angles are dimensionless. So in fact, you see that the length squared, 1 over length squared comes from the 1 over r squared. So I'll pull that out, and then here I have 1 over sine theta, d theta, sine theta, d theta, psi. Let me put a curly bracket, plus I pull out the 1 over r squared. And here is a phi derivative, so actually the sine thetas cancel out. So it's just 1 over sine theta squared, d phi squared psi. Okay. So remember I said something about the metric on the sphere. Okay, so if I call that if I call that H, let me call it Hij, d, let me call it dyi, dyj. So metric on unit 2 sphere. This is now d theta squared. So y1, let's call it y2. y2 equals to d theta, is theta. And then y3 is phi. Then this will be sine theta squared, d phi squared. Okay? And so what I claim is that this can be in fact written as 1 over r squared. Let me just write this down. And then this is 1 over r squared. And this is actually the Laplacian with respect to the sphere, the 2 sphere of unit radius. So which I'm going to call Laplacian as 2 acting on sine. Okay, and let's check that statement. Let's check that statement. Okay. Okay, let's check that statement here. Remember, it's the same rule, which is why I'm talking about it. It's the same rule. Now, and whenever you're calculating a Laplacian, first the question is, what's the metric? What's the inverse metric? What's the determinant? And once you know that, you can calculate it. Okay, so H, determinant of H, Ij, this is just a 2-dimensional metric. So it's just the 1, right? So this is represented by the matrix 1 and then sine theta squared. Okay? And so the determinant is just sine theta squared. And so therefore square root h is just sine theta. Okay? And then hij, which is the inverse, is just given by 1 and then 1 over sine theta squared. Okay? And so now we can actually check what's the Laplacian with respect to the sphere. Well, 1 over root g, 1 over root h is 1 over sine theta, d theta, sine theta. Again, this is root h, and then h theta is 1, so it's 1 times d theta psi, and plus 1 over root h is sine theta, d phi, root h, and then now 1 over sine squared theta, so it's 1 over sine squared theta, d phi psi. Okay? And so altogether, again, that's g phi phi, so now h phi phi, so now you can write it down, 1 over sine theta, d theta, sine theta, d theta psi, and then again, this is the phi derivative, so the sine theta cancel out, but you will pull out the 1 over sine theta squared, and then d phi squared acting on psi. That's exactly this guy over here. Okay, so the same formalism, but whatever coordinate system you're using, the formula works. All you have to do is make sure you know how to calculate, how to write down the metric. Okay? Any questions for me? So what we have realized today is that this operator is the negative, it is still the negative square of the linear momentum operator, right? So remember, this is still the negative p squared of psi, okay? just that we wrote it in a different coordinate system. But that's why I need to invoke differential geometry, so that we can know how to calculate it in any coordinate system we want. But later on, we will also discover that this guy itself will, so next time, because we're, I think, out of time soon, we will discover that the Laplacian on the sphere itself is actually what we would call I should call it L squared. The orbital, the square of the orbital angular momentum operator. Okay, so this is what we will discover the next time. And the connection is not completely obvious, right? But you should not be surprised because all of these derivatives involve only angular derivatives, right? So all these are thetas and phi derivatives. And what you discover is that these derivatives come from squaring L, and L itself is exactly what generates rotations on the sphere, right? And anything that generates rotations of the sphere should not have R derivatives. It should not have radial derivatives, because remember, derivatives are related to Taylor expansion. And Taylor expansion means you're trying to move. You're trying to move in that particular direction, right? If you're doing dr derivatives, R derivatives would mean you're trying to move in the R direction. Theta derivative would mean you're trying to move in the theta direction. So if this L is supposed to generate rotations on the sphere, it better only contain derivatives with respect to theta and phi only, right? It shouldn't have any R derivatives. So at least it passes the 0th order check, so to speak, right? You can see explicitly this guy is this guy over here, and it only involves theta and phi derivatives and nothing else. No R derivatives in particular. Okay. Any questions for me? Yes.
In the first
the mess up?
the third quality.
This one?
Yeah.
1, 2, 3. This one.
In the first is the radial momentum and second is angular.
Good. Yeah, so something like that. Yeah, because it's p squared, right? Yeah, but we don't usually think about it in that way. But it is something like that. I mean, we don't exploit it, but it is, roughly speaking, it is PR. It's PR. Yeah, it's PR. Yeah. Any other questions? Not, I'll see you guys next week.